Thank you, Osvaldo, for the introduction. Sorry. Just a moment. Okay, so for the last 20 years, I've been mostly engaged in controlled growth of functional nanostructures with the aim to affect the resulting properties of those nanostructures, not by the starting material, but primarily by affecting the size, nanosize, shape, and positioning on the substrate. And for example, we now have an ongoing project with Amit on magnetic nanostructures funded by Israel Science Foundation. But today I've decided to talk about a different topic, which I find also very interesting. And that topic I got exposed to during my sabbatical year at HP Labs in Stan's group. And that's what I call materials science and technology of memristors. I'd like to start by acknowledging my colleagues at HP Labs. And first and foremost, of course, Stan Williams, for having me there for a very fascinating sabbatical year. And I also would like to acknowledge our Israeli Ministry of Science, Technology, and Space for now allowing us to continue this research in Israel with two of my partners in crime, Shachar Richter and Arya Ruzin. So I'll talk about the conduction model we propose. I will show how we corroborate this model, the hypothesis, and I'll talk about some applications if the time permits. All right, for those of us who are not familiar with the concept of memristors, so we know the four fundamental circuit variables: current, voltage, magnetic flux, and charge. And we know all the relations, almost all the relations between all of them, such as this. And of course, from that, we derive the three passive circuit elements, which are the resistor, capacitor, and inductor. However, there is nothing in this quadruple. And more than 40 years ago, Professor Lian Chua has suggested that just out of sheer symmetry, there must be an element here that gives the relation between magnetic flux and charge. And he called it a memristor, or a memory resistor. So, in fact, of course, in the linear case, memristor reduces just to the simple resistance. However, if a memristor is a function of some state variable, which is time-dependent, for example, as defined here, and if we take an example that the state variable W is defined like that, then obviously from the definition, we understand that we talk about charge, or charge-dependent resistance. Now, the nice thing about this is, and that's the model that Stan suggested at the time, to explain this, there's just two potentiometers connected in a series. And then if you want to see the voltage division on this, the voltage division looks like that. And this is the memristance. And it will depend on the length of of course, of the potentiometer here, each potentiometer. So in 2008, HP Labs were the first to realize not just the theory, as Chua suggested, but the real memristor effect by having a titanium oxide partially doped. And the explanation is, in this model, is that we have a doped region and undoped region. Of course, doped region is a good conductor, and the undoped region is a bad conductor. And then during the biasing this, we will have motion of the dopants, and the dopant region will increase, and therefore we will have change of resistance. And the expression for this voltage division is zero. The resistance is here. And if we assume that the high resistance, the R off, is significantly higher than R on, it simplifies to this expression, and this is actually the memristance. Now, the interesting part about this is that in such case, the IV characteristic should have this so-called pinch hysteresis shape. And of course, this is the basis for switching. So we will have a low resistance state and a high resistance state, and we can switch reversibly between the two. And it's basically a very simple concept. We have a metal oxide, titanium oxide in case of the first Memristor at HP Labs, sandwiched between two metal electrodes. And by applying the pulse, we can switch it on and off reversibly. And the most effective in terms of density of the switching cells is the so-called crossbar geometry or a cross-point geometry, where we have the contacts in the types of crossbar, and then we can select and switch a particular cell by selecting the word and a bit line appropriately. Historically, that first memristor was from titanium oxide. And you can see the IV curve, the switching, the on and off switching here. And this is the crossbar. Later on, it was found that actually tantalum oxide is way better in terms of performance than titanium oxide. And that includes pretty much everything. Here we require electroforming first, which is undesirable. In tantalum oxide, almost no electroforming is required. The consumption of energy is extremely low. The switching speed is extremely high. We're talking about less than 2 nanoseconds for both on and off state, which is not characteristic for titanium oxide. Very high endurance, very high off-to-on ratio, which, of course, gives it the quality that we're looking for, the non-volatility, because the main application for this is actually non-volatile RAM. And ITRS has predicted this to be the next technology we're supposed to replace the flash that we all know and love. And the idea behind this is that not the entire insulating oxide layer becomes conductive, but under the influence of the biasing, actually some so-called conducting channels are formed during the electroforming step, and then they are, this is the forming step, so we have conducting channel. And then when we reset, we destroy this channel by increasing the gap here between the top contact and the channel. And we can rebuild it by putting the set voltage, by reversing the polarity, and rebuilding the channel. So the on-off switching that we saw here is basically by forming and destroying the gap between the channel and an electrode. Now, there are two types of switching, the non-polar switching or monopolar switching and the bipolar switching. In monopolar, we don't need to switch the polarity, just the magnitude of the bias. But I don't want to talk about this today. Today I want to talk about bipolar switching, where to get from the on state to off state, we need to switch polarity. And that's what we're talking about. This is characteristic of a titanium oxide, this sort of switching. So modulation of the gap between the channel and the electrode. However, as I will show you, in other systems, such as tantalum oxide, which is a better one, it's a completely different formation, mode of conduction. So my goals are here is to explore the material science and electronic processes in amorphous binary transition metal oxides. And I forgot to mention that these are amorphous, and as you will see, they were obtained by sputtering at room temperature. And in particular, the tantalum oxide is notoriously difficult to crystallize. So even to crystallize it during growth, we need a temperature in excess of 800 degrees centigrade. But it's not material to this topic because they work very well as amorphous ones. And therefore, by sputtering and then basically determining the composition and structure, we can understand then the properties, and then we can, I hope I will show you how we can employ these properties in order to make better or more interesting devices. All right. So this is the machine that I've been using for that year. And this is a very nice cluster tool. which consists of a sputtering chamber with load lock. And after sputtering the layers here, we could transfer, this is the backside of the machine, using this elbowed sleeve into the photoemission machine, and could measure the composition and electronic structure without breaking the vacuum in situ. And of course, this is a very powerful method, because when we knock out the electrons of our material, not only the core level electrons are knocked out, which allow us to determine not only chemical composition in terms of elements, elemental composition, it's more importantly, we can determine the chemical bonding, and we can actually determine the oxidation states of these materials. But at the same time, valence electrons are knocked out, and we can use this to determine the valence band or electronic structure and properties of the same material. So the materials I chose were tantalum oxide, and that's because, as I said, it's a working horse, but more importantly, and you will see this related to our model, it has extremely simple phase diagram. It has a solid solution of oxygen and tantalum on the one hand, and the terminal phase is the so-called alpha tantalum pentoxide, and that's it. So all this range is supposed to be just a mixture of these two phases. On the other hand, the other system I've selected were niobium oxide. Niobium oxide is more complicated because it also has those intermediate phases, so intermediate, and we will see that it's material to the model I was talking about. And finally, I chose tungsten oxide, and it has even more complicated phase diagram, because this region here expands. If you blow it up, you will see there are lots of very close in stoichiometry phases, which are called Magnelli phases. So these are three typical systems that I've explored. All right. So what happens when we start? We started to by sputtering the metal and then progressively mixing oxygen into argon and getting more and more oxygen to the film. We can see here this is the for tantalum, tungsten, and niobium. And of course, we begin with the pure metal. So we have here a pure 4F or 3D in case of niobium doublet. And at the same time, of course, we see in the valence band the famous protruding D band, and no valence band, of course, because it's a good conductor. And then as we mix in more and more oxygen, what we see is the formation of oxides. And as we put more and more oxygen, we see more and more oxides are formed, and they're conveniently shifted to the higher energies by at least 1 electron volt. So it's very easy to deconvolute them from those peaks. And at the same time, what we see in electronic structure is that this D band goes down, and as it expands, we see the formation of valence band that grows as the D band shrinks. And this process continues until we get fully oxidized layer. Here, you see we no longer have that D band. We only have the valence band that's supposed to be in an insulator, and no more intermediate oxides. We only have the finite terminal oxide. So pentoxide, pentoxide, and trioxide. Sorry, pentoxide, pentoxide, and trioxide. And because we see this very nice pumping of intensity from one peak to another, basically I assumed here, for the sake of the model, that the intensity of both of them is 1. So one is complementary to the other. And now, if we have this, and this is the power of XPS, we can deconvolute quantitatively out of those mixed states. We can deconvolute how many of them we have in our film. So we have basically the initial metallic state, finite, fully oxidized states, and intermediate oxides, the so-called mixed valences in between. And now this is the analysis, and we can see that as I put more and more oxygen in the plasma, we have more and more oxygen in the film. This is the RBS, which we use to calibrate our XPS. And you can see a very good correspondence between the oxygen and metal composition in the films. So the more oxygen we put in the plasma, the more oxygen we have in the film. And as this happens, what we can see is the rise of the valence band and the reduction of the D band. And now, if we do temperature-dependent transport, then for that one, we have to take the sample out and put it in the probe station and measure temperature-dependent resistance. And we see that as we put more and more oxygen in the film, and the valence band grows, then we can scale with the valence band, for example, the transport. And we can see that the resistivity grows and the temperature coefficient of resistance decreases. Now, of course, we know that metals have positive temperature coefficient of resistance, and semiconductors and insulators have negative temperature coefficient. And then what we could also do is to try to fit the temperature dependence of conductivity. Now what you can see here is the Ilan conductivity as a function of temperature to the power of -4. As you can see here, very, very nice fitting in all three metals. And now, why did I scale it with the temperature to the power of -1/4? Of course, that's because of the Motz and Anderson model of the Fermi glass. So the Fermi glass, the way I imagine this, is a raisin cake. And if you imagine that every raisin is basically a conducting center, and all the rest in between is just an amorphous insulating mass, then in terms, we can talk in terms of localization, what we have, and you see here the localization radius of each conducting center, then the conductivity will no longer be a metallic one, but it will be a hopping conduction. And it starts with the variable range hopping, where the electron can hop not only to the center nearest to it in space, but also to the one nearest to it in energy. That's basically, for this concept, Mott and Anderson received the Nobel Prize. And they defined, this is just parenthesis. Sorry, I haven't noticed that. In that case, there will be the exponential dependence of conductivity on the distance between or the length, or the separation lengths between the centers, and the activation energy for hopping. And we can put it logarithmically, and then we can feed the conductivity to the temperature to the power of -p. -p is a dimensional argument. So in other words, in a three-dimensional case, so three-dimensional variable range hopping, we're supposed to get the -1/4 dependence, and that's what we got. So we could safely say that what we see is a variable range hopping. And therefore, that oxide is basically a Fermi glass. Now, if this is so, by extracting the slope, we can actually get the density of localized states at the Fermi level from here. And if we have the density of the localized states at the Fermi level, we can get also the hopping length and hopping energy. And that's what we did, and you can see it here tabulated or in the graph, in this plot. And we can see there is a huge raise of hopping lengths, which basically indicates or signals the transition from metallic conduction to hopping conduction. And then later on, when the localization grows further, of course, we have the transition from variable range hopping to so-called nearest neighbor hopping, because when the conducting center is too far away and the overlap of the wave functions is very small, it's unrealistic to expect any other than just hopping to the nearest neighbor. And that's what we show here. And furthermore, until when this continues, so if the localization grows infinitely large, then obviously even the percolation will not be able to form the conduction. So we can use the percolation equation here, conductivity, where X is the concentration of the conducting center, X is some critical concentration below which no percolating pattern will be able to form. And what we see here from fitting here, so the fit on tantalum oxide is quite perfect, unlike in tungsten oxide, or even worse in niobium oxide. And in tungsten oxide, we get exactly the parameters for the classical three-dimensional percolation, with the critical percentage of conducting centers should be about 15%, and the power is about 1.5. We can see that in the case of niobium oxide, we see that it's, on the one hand, it's like two-dimensional percolation. On the other hand, it's like three-dimensional. 3D and 2D like. So this is the kind of mixed conduction. This is 2D, this is mixed 2D, 3D, and here it's complete overestimation. All right, so what's the model? Very simple. We have, starting with the metal, very, very nice overlap of the wave functions. Localization is nowhere near. Characterized by the very clear and single metallic doublet and the D band at the vicinity of the Fermi level. Then as we begin to oxidize, localization grows because they become more sparse. And then we can see it in XPS by formation of mixed oxides and the beginning of the formation of the valence band. And it continues. And of course, the localization grows more and more as we oxidize more and more. Eventually, of course, even the percolation pattern that can form with very strong localization will break down, and that last evidence, which is the defect band here, will disappear, and we will end up with a pure insulator. So here we have a pure metal. In the end, the terminal pure insulator, but the interesting region here in the middle is the Fermi glass behavior, which is the Hoping conduction. And we can actually understand what are these conducting centers. There is a nice paper by Ram Prasad who calculated all the possible oxygen vacancies in the energy spectrum within the band gap. This is 4 electron volt. This is roughly a band gap of tantalum oxide. And you can see here that our band is about 2 electron volts above the Fermi level. And according to Ram Prasad, this 2 electron volt corresponds to this oxygen vacancy from the so-called in-plane site that connects the basic polyhedra. And so what's going on is very simple. And this, all right, very simple. We have a conducting phase, a non-conducting phase, and in between, in the Fermi glass region, we have the mixture of them. And the resistance changes correspondingly to the relative proportion of the two phases using the lever rule, simple lever rule. Now, what can we do with this? So we can, if we understand that oxygen or oxygen ions coming in and out of the channel are the ones, because, I mean, the claim is that that's what happens in the conducting channel. Perhaps I forgot to say that. So the conducting channel gets oxidized or reduced when we apply positive or negative bias. And we want to show this. And the way to do it, we can switch the device to the on state, and then we can take it to TM. This is the device, by the way. And we can locate the channel using the so-called pressure-modulated conductance microscopy. So in this method, we measure the resistance of our oxide layer, and we scan it with non-conducting AFM tip, which just applies pressure. And then when it gets to the conducting channel, the one that used for switching, there will be a resistivity dip. We can take this tip further using focused ion beam. We can dissect it. And then we see the conduction channel here. And then we did EELs on this region. And EELs shows very clearly the reduction of oxygen as we go from the outside conducting channel towards the center of conduction channel. Oxygen goes down. So after the switching is oxygen poor. And we can also see it if we check the oxygen concentration around here. We can see again that the oxygen concentration goes down as we go towards the center. Just want to draw your attention to this little detail. Everything here is amorphous, except here we can see a crystallite. And that crystallite happens to be a high-temperature pentoxide phase, the so-called beta. So its formation energy started at 800 degrees centigrade. And also, using X-ray spectral microscopy, you could see the tantalum-rich core and then the tantalum oxide exterior. So this is the reservoir, which is used to exchange the oxygen between the core. And we can see clearly how it works. So this is the change of resistance, all right, as a function of oxygen percentage. And we see the metallic part with low resistance, insulating part with high resistance, and in between, we see the mixture of the two phases, and the resistance varies accordingly. The possible application with this is that in which case we can control how many oxygen atoms we actually put into the conducting channel by using the so-called 1T, 1M circuit one transistor, one memristor. So by gating here, with different voltages, we can control how many atoms we put into the conducting channel. And the result is we have here a multi-state switch, not only binary on-off, but we can control it, different states here, simply by using these different gate voltages. We can actually count how many atoms we have in the channel if we know the shape and the volume of the channel. Now, we assumed here, for the sake of simplicity, a simple cylindrical channel. So this is the core. This is the oxygen reservoir, namely the oxide. And we can find the scaling factor here. So by doing that, we can actually see how the resistance corresponds to the percentage of oxygen in the channel for every state that we can see here. And as I said, knowing the volume, we can calculate, and we can see, for example, that for a gate voltage of 2 volt, we have about 21% of oxygen, and that results in 10 times to the 4 of atoms in the channel. And by going to 1.7, we have 32%, which is 10.5. So we can control the oxygen, the number of oxygen ions in the channel with the precision of thousands of atoms. I think it's pretty nice. And the HP, of course, immediately patented this. So in our model, this is what happens. So the question is how the oxygen gets in and out of the channel. So of course, what initiates it is the electric field. When we apply plus, so the bottom electron is platinum, which is neutral. Top electron is reactive. So when we apply plus to the tantalum electrode, of course, it attracts the oxygen ions, anions upwards. And at the same time, if you remember that crystallite, that means that very high temperature revolved there during switching. So there is a thermal field as well, which is called the Surrey effect or thermophoresis. And thermophoresis works annually. So the atoms or the ions, basically the vacancies diffuse towards the higher temperature region. So if we switch on, the oxygen and ions begin to move upwards and then swept out annularly by the Surrey effect. And vice versa, if we change the polarity and we put minus here, so it drives the oxygen atoms down, and the thermophoretic field drives them in. So this is pretty much it. I won't talk about other things. I just wish to thank you for your attention.